All right, let's talk about 25.6 and 25.7. So continuing on with geometrical optics, where initially we just simply talked about if you have a flat plane, you'll have an incident angle and reflected angle, incident and reflected there compared to that normal line. Again, you always draw that normal line. Secondary, if you have water or something like that and you're going from air to water, you're going to have a light ray come in and get refracted. And again, the first thing you want to do is draw that line there. Oops, and there's your incident angle. Nope. There's your incident angle. What's going on here? What am I sitting on? Incident angle. What's going on here? Done. Not sure. Oh, I'm sorry. I'm up in the margin. Okay. Incident angle and refracted angle. Okay, so that's Snell's law there. So those are your two things where you're moving against nice flat surfaces. Well, what happens if this water is curved? What kinds of cool things can you have happen? And that's where we get lenses like glasses on your face or lenses in a telescope or something like that. There's two main types of lenses. There are lenses that are curved like this and lenses that are curved like that. So light can either hit the surface this way and bounce off or pass through or whatever, or light can go this way and bounce off or pass through, and you'll have different effects depending on different ones. Okay, so there's some vocabulary to deal with a lens. This type of lens here is a converging lens. This means it's curved this way. And what it means is it causes the rays of light that come into it to converge to a point. Okay? That's what a converging lens does. It causes the rays to converge together, and that's like if you put a magnifying glass to set some leaves on fire or something, then that is how that works. So there's a couple key vocabulary points with a convex lens or any lens. So first of all is the type of lens. So this is a convex lens or a converging lens. The focal point is the point where the rays will converge, and that were parallel rays. When the rays come in like this, they're going to cross at that point, and that point is called the focal length. And it's this little, well, capital F is the focal point. The distance from the center of the lens to that point is the focal length of the lens, and F is the is a distance. It's a measurement in meters, centimeters, or some other distance like that. Okay. The power of a lens is just 1 over the focal length. So whatever you measure for your focal length, if it's 2 centimeters, 3 centimeters, 10 centimeters, whatever, 1 over that is the power of the lens. Okay, and that's measured in something called diopters, and diopters are what, when you go to get your glasses at the eye doctor, they measure the strength of the lenses in diopters. Okay, and it just has units of 1 over m. So let's say you've got a focal length of 8 centimeters on your lens. What's the power of it? It's 1 over 0.08, and so that tells you that it's 12.5 diopters. So that means that this distance here would be 8 centimeters. Okay, the other type of lens is a diverging lens, and so they cause the rays, when they come in, instead of converging, they diverge away from each other. So that's just a different type of lens. It also has a focal length, but it causes your rays to do other things. So, when you get to complex systems, you could have a lens like that followed by a converging lens, and that would help deal with some of the chromatic aberrations that you have, because it would diverge out a little bit and then reconverge it, and so it can, make all your dreams come true. All right, so ray tracing is the concept of treating light as rays and then tracing some rays to figure out where images are going to be created by a lens. Okay, so we treat lenses in this course as thin lenses, which means we don't have to consider the thickness of the glass when we're considering how the rays behave. So we're imagining they just come in and they are reflected or refracted through them, and then we don't have to deal with the slight, if you have a really thick lens here, you're going to have a refraction and it's going to travel for a while and then it's going to be refracted, so that's going to shift the focal points around and other things. So we're just going to treat them as thin lenses. Okay, so a thin lens is just very thin. You don't get dispersion and other aberrations, so we're just imagining it's a very thin lens. And okay, so your two lenses, now the rays are coming in from the right side of the screen. So this is say it with me, a converging lens, because it causes the rays to converge at the focal point. A diverging lens, the rays come in and they diverge away, as if they came from the focal point. Okay, so those are just the two main types of lenses. Okay, there's let me get rid of this. Okay, so a ray that goes right through the center of either lens will continue on, whether it comes in like this or that or whatever. A ray that goes through the center of the lens will just continue on as going on. So there's some ray tracing rules here, so read about those, and these are the 5 rules for how rays are created, and those are what are kind of pictured here in this diagram. So the first ray that you can draw is one that goes straight into the lens. When it goes into the lens, it refracts through the focal point. The next ray just goes straight through the center of the lens because it's not refracted at all. So I'm going to draw that up here, pink. And then the third ray is going to be the one that's going to go through the focal point on this side of the lens. So there's symmetric points. The focal point is the same on both sides. If it goes through the focal point on this side of the lens, it will come out, well, this messed it up. It will come out, boop, and then come out straight on the other side of the lens. And with those 3 rays, you can see that this lady standing here is going to be teensy tiny on the other side of the lens and upside down. Okay, so her image through this lens, she's going to end up upside down. So those are your 3 rays, and you have to learn those. Those are the 3 rays you have to draw. One going straight into the lens, goes bent through the focal point, one that goes straight through the center of the lens, and one that goes through the focal point on the other side of the lens and then gets bent out straight. Okay? Now, the calculations that you're going to do, so your first goal is to be able to draw these things and determine where the image is going to be created. Your second thing is going to be able to calculate where the image is going to be and how tall the image is going to be, or how compared to the real thing. So there's a couple measurements you need to be concerned about here. First one is the focal length of the lens. You already know that one. The second one is the image distance, DI, and the object distance, DO. The object distance is literally how far away is the lady from this giant lens. The image distance is how far away from the lens is the image created. Both of those are distances, 10 centimeters, 20 centimeters, for example. The H0 is how tall she is in real life. HI, it's actually HO, height of the object. Height of the image here is the magnification, basically how much smaller she's going to appear. The ratio is the magnification, okay? So this image here, there's 2 types of images you have to pay attention to. Real images or virtual images. This is a real image, and that's because the rays themselves intersect at this point. The rays all intersect at that point, okay? And yeah, this is just showing how a camera works and how your eyeball works. Okay, so what I talked about up here, first thing you have to do is be able to draw these diagrams. Next thing is you have to know how to use these 3 numbers, F, DI, and D0, or DO. So there's an equation, it's the thin lens equation, and it relates all 3. And it says 1 over the distance object is equal, plus 1 over the image distance is equal to 1 over the focal length. So if you know your object and image distances, you can calculate the focal length of the lens. If you know where your object is and you know the focal length of the lens, you can calculate where the image is going to be created. All three of these are measures of distances, and so you're able to plug them in and determine the distances. Once you figure out the object and image distances, the ratios of them are the magnification. It also turns out to be the same ratio as the object and image heights. So you can use DO and DI to figure out the magnification, and then if you know how tall your object is, you can figure out the height of the image based on that. Okay, so those are your two equations that you have to know and love. Here they are again. And again, these, they're literally how far away from the lenses are these things, okay? Here's an example, right? You can calculate what these are going to be here. There's just different, we've got, there he is, he's upside down. You can see in that image that the guy taking the picture is upside down. Here, just a big eyeball zoomed in. Okay, now, so I think this one is if your object that you're looking at is within, so this focal point is that far away, which means it's over here, about there on this side of the image, or on that side of the lens, which means our object is within, in between the focal point and the lens. If that happens, your three rules still apply, but now you're going to get what's called a virtual image. And that's because the image appears to be here. These dotted lines mean the rays appear to be coming from those points, and they're not really. So that's what we call a virtual image. Okay, but you have your same equations. Okay. Let's see here. Okay, so now you've got a diverging lens. You're going to do the same thing. You're going to have your three rays. First one goes in and diverges out as if it came from the focal point. Next one goes straight through the center. Third one, well, actually, that's all you need. Those two will help you determine that your image is there in that little point. Okay, and you have the same thing, image distance, object distance, and you can solve for, go through these examples here. The trickiest thing with these lenses is remembering the signs for the objects in the images. Generally, if the object and the image are on opposite sides of the lens, both of them are positive. If the object and image end up on the same side of the lens, one of them is negative. If the diverging lens, in the case of a diverging lens, the focal length of a diverging lens is always negative. So if you are told that a lens has a focal length of minus 10 centimeters, since it's minus, you already know it's a diverging lens and not a converging lens. Converging lenses always have positive focal lengths. Diverging lenses always have negative focal lengths. Okay, and so you can see in this that the image and the object are on the same side of the lens, so our image distance here is negative. So that's just, you'll have to do a couple of these problems to get the idea of what these values are. Now, if the magnification is negative, then the image is upside down. If it's positive, then the image is right side up. You've got some problem-solving tips here. Read that. Mirrors, image formation, same idea. It's law of reflection, so it's pretty straightforward. Parabolic mirrors, or spherical mirrors, actually. This is, I don't think it's a parabola. I think it's just a spherical mirror. You'll have, yeah. So this is a spherical mirror, and it's showing this concept of spherical aberration, where the rays don't all converge at the single point. They kind of smear along this line. If you look only at rays at a small section of it, then they all converge. So if your thing is small enough, you won't have spherical aberration. If it's a parabolic mirror, you'll fix that, but that's a more difficult shape to make. If your mirror is flipped around so your shiny part is on the other side, like one of those mirrors at a gas station to see around the corners, then the rays will appear to be coming from the focal length on the other side. Okay, same thing, concave reflector. You've got same equations. and so on. So we have the solar panel there, solar cell. So these mirrors here for beauty mirrors or whatever they're called, those mirrors, they zoom in a lot and allow you to see your face. A lot of hotel rooms have those or whatever. Here's one of those security mirrors that help you see around corners and other things because of their shape. Okay, all right, so I guess we don't have a summary here. But 25.6, we got image formations from lenses. 2 types of lenses, converging, diverging. Make sure you know your 3 rays for your converging lens, your 2 rays for your diverging lens, and then make sure you know your thin lens equation and your magnification equation, and be able to calculate where the objects and images are. Okay.